Welcome. This question says, consider the circuit that consists of a 20-volt battery, an 18 Henry inductor, a 6 ohm resistor that are connected in series, and what current flows through the resistor 2 seconds after switch S1 is closed. So let's just draw this circuit out. We have a battery. Let's assume that the switch has just been closed, so I don't need to show it. And I have my resistor. I can show it either symbol. So this is my L. Oops, a daisy. This is my L and this is my R. Sometimes, for instance, when I lived in Europe, we would show the resistors as a symbol like that, and in the States we use the more traditional symbol of the zigzag line. This is 20 volts. This is 18 Henry. This is 6 ohms. And what's going to happen? Conceptually, what's going to happen is that at a certain time you're going to close that switch, and you might think, if I'm plotting time and I'm plotting current, you might think that instantaneously you would get a rise in current. But what happens is, because of the inductance, what you get is a back EMF that slows the increase in current. And so we say it takes a time to energize the system. And so we need some way of describing that. And what we say is that the current at a given time is equal to, what would it be in the end? In the end, well, V equals IR. In the end, I equals V over R. So that would be my EMF over my resistance. That's what it's going to be in the end, but that is modified by a transient effect, and we can represent that by 1 minus E to the minus the time over a thing called a time constant. And the time constant is the time, it's the little bit of time it takes for the current to get to 63% of its maximum value. This is Imax. The time constant is the time it gets to that point there, which is 63% of Imax. It's a very nice way of characterizing LR circuits. And I also know that my time constant equals L over R. So I can say, okay, let's put some numbers in. My current at a time of 2 seconds is equal to my EMF, which is 20, over my resistance, which is 6. And this is modified by 1 minus E to the minus the time over L over R. I'm going back into doing letters there, so let's just stick with numbers. The time, and the time, of course, that we're interested in is 2 seconds, so that would be minus 2, and L over R would be 18 over 6. So then this is I at 2 seconds is equal to 20 over 6, 1 minus E to the minus 2 over 3. So I get my calculator and I go second, I get to E to the X, and then my E to the X is minus 2 divided by 3. I can do that. Enter. And then I say 1 minus second answer. Enter. And then I multiply that by 20, enter, and I divide that by 6, enter. And what I get for this at 2 seconds is equal to 1.62 amps. Let's get a feel for this my time constant equals 18/6, which equals 3 seconds. So at 3 seconds, I should have reached 63% of my maximum value. And my maximum value, I max, which equals 20/6, is my EMF over R, which equals, what, 3.3 amps. So maximum value is 3.3 amps. I should be less than 63% of that, and 1.6 divided by 3.3 is equal to 48% of that, which kind of makes sense. I'm somewhere here. I'm somewhere in there. So there we have it. It's basically just remembering an equation, knowing what the symbols stand for. And it's nice to be able to represent it and know where you are on this transient curve. So there we have it.